Okay, let's start with RSA algorithm. Okay, okay, let me just choose the right settings. Yeah, RSA algorithm. Okay, before we begin with RSA algorithm, let us quickly understand or briefly understand where does RSA sit in the hierarchy or in the field of cryptography. So within cryptography there would be various algorithms, but broadly we classify algorithms into two parts, which is a public crypto system and the other is um, symmetric crypto system. So public crypto system is also known as asymmetric crypto system, and the symmetric being the other part of cryptography. So the asymmetric crypto system or the public crypto system is basically there we will have two sets of keys, public key and a corresponding private key. We'll use public key for performing one operation and the corresponding operation will be performed by the private key. So for instance, encryption and decryption, public key will be used for encryption, and when we have to decrypt a message, we will use the corresponding private key. So that is the public key crypto system. RSA is one such algorithm in the public key crypto system. There are various other algorithms such as DSA, elliptic curve, which is ECC, and others. In this video, we will go ahead and discuss about RSA crypto system. So in the RSA algorithm, okay, before I go ahead and explain RSA, let us understand something known as Euler's Totient function. Okay, because this is something which we will be using here. So let us first understand this Totient function. Okay, so the Euler Totient function is basically is represented by phi n, which is equals to the size of the set Zn star. Okay, now what do we mean by this? All right, so let us first understand what is Zn star. So Zn star is basically, Zn star is defined as A belongs to the set of Zn. Mind it, here there is no star, here we have put a star, such that GCD of A and N is 1. So basically we want to find out all the positive integers. So here the number starts from 1 till n, all the positive integers from 1 to n which is relatively prime to n, right? So what do I mean by this is, let us say n is 15. Okay, let us assume n is 15. So now Z15 star is what? So all the numbers starting from 1, 2, 3, all the way till 15, all these numbers, if they are relatively prime to 15, then they will be part of this group. All right, and what do we mean by relatively prime? Well, relatively prime means prime. So for instance, A and B, okay, are relatively prime if and only if GCD of A and B is 1, right? So the GCD, so basically GCD is greatest common divisor. Between A and B, the greatest common divisor is 1. There is no other divisor there. So such numbers are relatively prime to each other. Now let us quickly fill up this Z15 star. So 1 and 15, the GCD is 1. 2 and 15, the GCD is 1. 3 and 15, the GCD is 3, so 3 won't be there. 4 and 15, the GCD will be 1. 5 and 15, again GCD is not 1. 6 and 15, GCD is not 1. 7 and 15, GCD is 1. 8 and 15, GCD is 1. 9 and 15, GCD is not 1. 10 and 15, GCD is not 1. And 11 and 15, GCD is 1. 12 and 15, again not 1. 13 and 15, it is 1. 14 and 15, it is 1. So these are the elements of the set Z15 star. Let us now count the, now let us quickly say what is the size of Z15 star. Well, the size of Z15 star is 8, right? The numbers of element in Z15 star is how many elements? 1, 2, 3, 4, 5, 6, 7 and 8. So that is why Z15 star is 8, and this is something which is denoted by the Totient function phi n. Here n is 15, so this is what phi of 15 is. Okay, so this is known as Euler's Totient function. Alright, so when I was forming this group Z15 star, I said like 5 is not there, 6 is not there, 7, 5, 6, 9. These elements are not part of the group. Let's just quickly understand why it is not there, even though it might be very clear to you, but let me just quickly talk about it. So 3, 5 and 6 are the elements which are not part of the group Z15 star. And why is so? Now to understand that, let us try to compute the GCD of 3 and 15. Well, the GCD of 3 and 15 is 3, right? Which is not equals to 1. That is why it is not part of Z15 star. And the same goes for 6 and 5. You can do it on your own. Okay, so now let's, okay, now we have understood the now we have understood what is Z15, and we have also understand what is the meaning of phi n when we say phi n is 8. Now let us write an equation for this one. Now for smaller numbers such as 15 or some other number 14, 20, it might be easy for us to go ahead and write down all the elements of the set and then count the number of elements and come to a conclusion कि, okay, the size of the set is 8 or something else, right? But what will happen if n is very large? So for n, when n is very large, we have an equation denoting that Totient function. So the phi n is basically defined as n into products of p, where p is prime. Okay, I'll explain what do I mean by this. 1 minus 1 over p. All right. So what do I mean by this is that, so for instance, in our example, n was 15. Now when I say p is prime, what do I mean by that is that find all prime factors of 15. So let us try to find the prime factors of 15. What are the prime factors of 15? Well, if you go by this, if we compute the LCM of 15, this is what we get, which is basically 3 into 5 into 1 is 15. What are the prime factors here? These are the prime factors, right? This is a prime factor, this is a prime factor. So the prime factors, when we say p is prime, then the prime factors are basically 3 and 5 for 50, right? So now let us plug these values into the equation and try to find out the value of phi n. Now phi n is basically, let me just scroll a little bit up so that we see the equation. So phi n is basically phi of 15, which is equals to 15 into, so the first prime factor is 1, right, and the other one is 5, right? So this is the equation, right? Now if you go ahead and solve this equation, what do we get? Phi of 15 is 15 into 2 by 3 into 4 by 5, and this is basically 8, right? So that is how we come to 8. That is how 8 is derived from this equation. So this is the equation. Let me just put it into a square. Okay, all right. So this is what the equation is, right? Now, having understood what is a Totient function, let us take a special case of Totient function. What will happen? And that special case is basically, let me use this. What if n is prime? What will happen in such cases? What will happen to Totient function when n is prime? What will happen to phi n? Okay, so when n is prime, all right, let me just scroll up a bit. When n is prime, when n is prime, what will be the prime factors of n? The prime factors of n will be n itself, isn't it? That will be the only number which will, so for instance, let us take an example here. Let me just scroll a little bit here. So for instance, in example, let us take n equals to 14. Now if you take an LCM of 14, it is nothing but 14 times 1, right? Which is 14 into 1 equals to 14, and this is the prime factor which I have, right? So the prime factor will be n itself, isn't it? Now what will happen to the equation when the prime factor is itself? Phi of n, and here n is a prime number, so n into, what will happen here? Since we have only one prime factor, which is n itself, so this is what we can write it down, which if we solve it further becomes n minus 1 over n, and n cancels, and this becomes n minus 1. Alright, so phi n equals to n minus 1 if n is a prime number. So this is the thing which we will be using in RSA, and that is why I went ahead and explained you all these things. So this is something which we need to remember, which is if n is prime, then phi n is n minus 1. All right. Okay, so now that we have understood the Euler's Totient function and uh, its unique case, which is what will happen when n is a prime, let us now try to understand the RSA algorithm. Okay, so let me begin with RSA. So in the RSA algorithm, we start with two prime numbers, P and Q. These are our prime numbers. Okay. Once we have the prime numbers, we go ahead and compute something known as modulus, which is represented by n, and modulus is n equals to P into Q. And this, by the way, is modulus. Let me just write it down here. Okay, so this is our modulus. Once we have the modulus, here we go ahead and compute the Totient function, the function which we have just saw. So the Totient function, which is phi n, is what? What will happen here? So the phi n is phi into P into Q, which is equals to phi of P into phi of Q. Okay, wait a second. Phi of Q, and this is equals to, from our observation, which is when n is a prime number, then the Totient function phi n is n minus 1. So when since p and q are prime numbers, so the Totient function phi is basically p minus 1 into q minus 1. All right. So this is our phi n. By the way, one very important thing to note, here we have distributed phi of p by q into phi p into phi q. This is not something which we can do always. This is possible only in this case when p and q are prime numbers. In the cases where p and q are not prime numbers, there will be some special cases, or it will be governed by a different equation there. All right, so this is something which we have to note of. Now, since phi n equals to, okay, till here we have phi n. Now once we have the phi n, we go ahead, one second, I need one more page. So once we have phi n, we go ahead and select a number e, which is known as, we go ahead and select public exponent. Okay, public exponent represented by e, and there are certain conditions on e. E should be greater than 2 and it should be less than phi of n. Okay, and this is one condition, and the second condition is, and GCD of e and phi n should be 1. Let's so choose any number which satisfy this condition and this condition, and that will become our e. So one common public exponent which we use in our practice is basically 65537. All right, and here if you want to understand it intuitively, now the phi n is basically p minus 1 into q minus 1, right? Phi n is what? P minus 1 into q minus 1. Now what will happen when you subtract 1 from a prime number? This will become an even number, isn't it? Right? And this also will become an even number. And the product of two even number is an even number, right? So we know that phi n will be an even number, isn't it? In this particular case, by the way, in this particular case where p and q are prime numbers, phi n will be an even number. So now if phi n will be an even number, then what should be the value of e? Let us assume, let us check. I mean, e could be an even number or an odd number, right? If e is an even number and phi n is also an even number, its GCD will be at least 2, isn't it? Right? I hope that makes sense. And so for that reason, and by the way, we want our GCD to be 1, right? So for that reason, e will be an odd number always. All the time, e will be an odd number. And this is one such odd number. Okay, so that is just one minor observation which you can deduce from by analyzing the nature of phi n and what should be the value of e. Okay, so once we understand what should be the phi n, what should be e, let us now compute what should be private exponent. So private exponent, which is denoted by d. Okay, now the private exponent d is ed congruent to 1 modulo phi n. Okay, this is essentially basically ed when divided by phi n gives 1 as remainder. This is what it means. This equation which we have written over there, this equation is basically this. ed when divided by phi n gives 1 as a remainder. Alright, so in that way we will be able to find out the value of d. D is something, in practice we use extended Euclidean algorithm in order to find D. I will make a separate video in order to understand the extended Euclidean algorithm. But for now, let's move forward. Okay, so that's pretty much it about the RSA algorithm. Now, basically now what we are left with is encryption and decryption. So the encryption is basically you want to get a ciphertext. So ciphertext is equals to plain text to the power public exponent modulo n, and that's how you get a ciphertext. Similarly, decryption is plain text equals to ciphertext to the power d private exponent modulo n. All right. So that is how you perform encryption and decryption using RSA algorithm. Let me quickly summarize this because I think the content was a bit high, was a bit lengthy. I'm sorry about poor wording there. Okay, where is my mouse? I can't seem to get a hold of my mouse. Okay, there you go. All right, so let me just quickly summarize it. So for RSA, we started with two prime numbers p and q. Then we have calculated n, which is equals to p into q. Then we calculated a Euler's Totient function, which is phi n, which is p minus 1 into q minus 1. Okay. Then we took e such that e is greater than 2 and is less than phi n, and GCD of E and phi n is 1, and then we had D, which is ED is 1 modulo phi n. Okay, once we had that, then we perform encryption and decryption, which is plain text, sorry, ciphertext. Ciphertext equals to plain text to the power encryption modulo n, and plain text equals to ciphertext to the power private exponent modulo n. Okay, so here we have seen various components, right? So this was our modulus, and then this was our Euler's Totient function, and then we have something called as public exponent, and then we have something called as private exponent. Okay, so now what is a public key here? Now the public key is basically a tuple which is composed of modulus n and public exponent e. Private key, or is also known as secret key, or the things which need to be kept secret, are composed of n and d. By the way, phi n is also needs to be kept secret. You cannot leak it. This is something which is available openly in the plain text format. This is something which is kept secret and it is not made available to public. So okay, that's about the RSA algorithm. See you in the next video. Thank you.